Hello. In this video, I will be covering an introduction to graphs in C++, continuing our series on fundamental data structures. So first of all, what is a graph? Well, a graph is a collection of vertices or nodes, which are the fundamental units or points. So for example, 0, 1, 2, and 3 are all the nodes or vertices. And then a graph also is a collection of edges or links. They are the connections between the nodes. So we have edge 0, 1, edge 1, 2, and edge 2, 3. Graphs can be undirected, which means edges have no direction. An example of that would be a friendship network on social media. So there's a mutual following and a mutual friendship there. We will be covering undirected graphs in this video. Directed graphs or digraphs are graphs in which the edges have direction. So an example would be Twitter follow relationships or X. So, for example, a celebrity might have hundreds and thousands of followers on social media, but that celebrity is not necessarily going to follow every single person back. So there's a one-way relationship there. We'll be covering digraphs in the future when we get to respected algorithms. Examples of graphs in real life, road maps. In this case, the cities would be vertices and the roads would be edges. Again, as I said, social networks, people's vertices, connections as edges. And then big in computer networking as well, where computers and routers are vertices and cables would be edges. So how do we actually represent graphs in programming, in general programming? Well, there's two ways. The first, shown on screen, is using an adjacency matrix representation. Here, we represent a graph using a 2D matrix. So, for example, adjacency matrix ij, if that's 1, that means that there's an edge between vertex I and vertex j. Since this is an undirected graph, we would set both adjacency matrix ij and ji. The output clearly shows which vertices are connected. So, for example, on lines 9 to 10, we have the link between 0 and 1. On lines 12 and 13, we have the edge between 1 and 2. And then on lines 15 and 16, we have the connection between nodes 2 and 3. And then here, we are simply representing the adjacency matrix. So let us compile this. And let us run it here. As we can see here, we have our adjacency matrix. So between 0 and 1, 1 and 0, 1 and 2, and then 2 and 3. So some advantages. This is very simple and direct. Checking to see if an edge exists between nodes is constant time, or big O of 1. But the disadvantage is that it takes a good deal of space, even if the graph has a few edges. This is inefficient for sparse graphs. So what would be better and kind of address those concerns? Well, an adjacency list. So here we're using an array of vectors. Each index in the adjacency list corresponds with a vertex. Each vector stores all adjacent vertices connected to that vertex. So, for example, vertex 1 has connections 0, and 2. The advantage, this is space efficient for sparse graphs. This only uses big O of the number of vertices plus the number of edges. This is also easy to traverse neighbors of a vertex. A disadvantage of this is checking if a specific edge exists requires a search, which can be big O of whatever the degree of the vertex is. So let us compile this example now. And let us run it here. As we can see, 0 only has an edge to 1. 1 has an edge to 0 and 2. 2 has an edge connecting it to 1 and 3, and then 3 only connects to 2. So again, a little more detail about directed versus undirected graphs. In undirected graphs, edges go both ways. If A is connected to B, then B has to be connected to A. In directed graphs, edges have a direction. If A to B exists, it does not necessarily mean that B is connected to A. Think of it as a two-lane road for an undirected graph versus a one-way road versus being a directed graph. An example, undirected, Facebook friendships, and then directed would be Twitter follows. Weighted graphs, sometimes edges have weights or cost. So, for example, in a roadmap, a weight could represent distance or travel time. This could be represented by an adjacency matrix with weights, meaning that non-zero values store the weight. Or it could be also represented by adjacency lists with pairs. So kind of a neighbor and weight mapping. Before we go, let's go through some key takeaways from this video. First of all, a graph consists of vertices or nodes and edges or connections. An adjacency matrix representation is very simple, but it takes up a good deal of space. However, in terms of time complexity, quick edge lookups are a plus. Adjacency list is kind of the opposite. It's very space efficient, but it takes a little more time complexity. But easy neighbor traversal is a plus. You can see a direct list of what nodes are connected to a particular node. Graphs can be directed or undirected, and weighted or unweighted. Choosing the right representation depends on whether the graph is dense or sparse and what operations you need to perform. In the future, in many different algorithms, there's many different implementations of graphs. So look out for that. If you found this tutorial helpful, do not forget to like, subscribe, turn on notifications, and leave a comment. Please reach out if you have any questions. Otherwise, thank you for watching and have a great day.